This video is on the last two pages of section 4.4, where we look at problems that unfortunately do not have domains that are closed intervals, and in this case we cannot use the EVT. So let's start off with example 7. What is the smallest perimeter for a rectangle of area 20 square meters? So we'll start off by drawing a rectangle. Let its dimensions be x meters by y meters. And we're told that the area is 20 square meters, so we know that xy is equal to 20. What are we looking for? We are looking for the dimensions that give us a smallest perimeter. So we need to set up an equation for the perimeter. The perimeter using both variables x and y is obviously 2x plus 2y. Remember, the perimeter is simply the length all the way around the four sides. We'll want to work in one variable, so let's, for convenience, work in terms of x. Y is 20 over x, so p using x only, so p is a function of x, is 2x plus 2 times 20 over x. So we get p of x is equal to 2x plus 40 over x. Next step is to look at our domain, as usual. Now let's see what's going to be true about x. In this case, compared to the previous examples, x cannot be equal to 0. And it's not because we're not going to get a rectangle. It's because if x is 0, then y will be infinite, it'll be undefined, as actually will be the perimeter. So we cannot have x equal to 0. But x does need to be positive. The question is there a biggest value for x? And the answer is not. If we look, x does not have to be a whole number. X could be 100, for example. That just makes y, if x is 100, y would be 1/5. So x can be as big as we please. The only condition is x has to be greater than 0. This means, since we do not have the domain being a closed interval with a function continuous on a closed interval, we cannot use the EVT. Nonetheless, we can still go ahead with the problem. There are no endpoints to consider. Any candidates for a absolute min will also be local. And so we're going to be looking at our critical points. So we need to find our critical points for p, which means I've got to differentiate p of x. Before I differentiate it, remember it often is helpful to rewrite the function. So I rewrite p of x. P prime of x is going to be 2 minus 40x to the negative 2. Let's write that, rewrite it one more time. Let's write p prime as a single fraction, common denominator is x squared. 2x squared minus 40. Okay, critical points, so where p prime is 0, if I set p prime equal to 0, remember a fraction is 0 when the numerator is 0 and the denominator is not. So 2x squared minus 40 is 0, 2x squared is 40, x squared is 20, x is either positive root 20 or negative root 20. Let's cross off the negative root 20 because it's not in our domain. P prime dne, when is that true? When x is 0. Again, cross it off, it's not in our domain. So in fact, we have just the one critical point. We cannot, however, assume that critical point is necessarily going to give us our absolute min. We have to justify that and show that. So how do we set about that? The first thing is to show it's a local min, and then we will also have to prove it is an absolute min. So remember, if you want to show something as a local min, we have both the first and the second derivative test. In optimization problems, it's often more convenient to go with the second derivative test, and it's a good time to remind you of that. So let's find the second derivative. I've got actually three different versions. This is worth talking about very briefly. Here are my three different versions for p prime. Of the three different versions, the first one is the most convenient one to differentiate a second time. So I'm going to take that p double prime of x when I differentiate. I'm using this expression that I'm differentiating. Derivative of 2 is 0. And then when I differentiate minus 40x to the negative 2, the negative 2 comes in front, making positive 80x to the negative 3. That's the same as 80 over x cubed. So p double prime of root 20 is going to be, when I plug in root 20, I get a positive answer. I don't care exactly what its value is, I can just see it's positive. And remember that if p double prime is positive, you have got a function that is concave up at that point. Remember, positive is a happy face. Let's draw a big smile. Concave is concave up with a horizontal tangent. I have got a local min. So therefore, p has a local min at x equals root 20. But now I have to also justify I've got an absolute min. Well, this is actually not as hard as you might think. Let's go back to p double prime. If you look at the expression for p double prime, you can see that depending on x, this will be sometimes positive and sometimes negative. However, it will always be positive providing x is positive. So let's write that down. P double prime is positive for all x bigger than 0. Therefore, p is, if p double prime is positive, it means that p is concave up everywhere in its domain, since the domain is x is greater than 0. So p is concave up everywhere in its domain, therefore the local min at x equals root 20 is also the absolute min. So we're now ready to go back and answer the question in full. We want to know what was the smallest perimeter, what were the dimensions. So let's have a look. If x equals root 20, since y is 20 over root x, y is 20 over, sorry, no, it's 20 over x, not 20 over root x. So it's 20 over root 20. Now you can simplify that by multiplying numerator and denominator by root 20, but a kind of neater trick is to remember that 20 could be made up of root 20 times root 20, and I was dividing by root 20, so when x is root 20, y is root 20. So I have my rectangle that is actually a square. The sides are root 20 by root 20. So my minimum perimeter, there are 4 equal sides, so it's going to be 4 root 20. And we could simplify that since root 20 is 2 root 5. That is 8 root 5. That step is optional, but it's good to be able to recognize answers in different disguises. And the dimensions are root 20 by root 20, or 2 root 5 by 2 root 5. And everything is measured in meters. And we are done. The key idea here, though, is if you do not solve using the EBT, you may not assume that your critical point automatically gives you the absolute minimum for the function. Although it may be highly likely that it does, you still need to prove you have an absolute minimax. So how do you do this? You need to show first if it's a local min or max using either the first or second derivative test. But then you also have to demonstrate it is an absolute min or max. And that very often we do by just establishing, if it is true, that the function is concave up or down, depending on the problem, everywhere in its domain. Couple of small points to make. If there is only just one critical point in the domain, and you have established that it's a local max or local min, as the case may be, can you assume that it's the absolute max or min? And actually in this case is yes. If there is only one critical point and you know it is a local max, it will be an absolute max, because if there are no other critical points, the graph cannot change direction and start coming up again. However, if there are two critical points, and one is a local max and the other is a local min, you may be tempted to say, meh, there's only one local max, it must be the absolute max as it's the only candidate. You need to be really careful. You cannot make that assumption, because look, here is a local max and a local min, and yet these y values are not the greatest y values, or at the local max is not an absolute max, the local min is not a local min. So moral of that little story is be very careful that you establish an absolute min or max correctly. All right, so let's set up the problems on the last page, and we'll do this as quickly as possible. The first problem, example 8, we've got a 216 square meters. Ooh, that is an area unit. So that's telling me the area of my rectangular p-patch. So I've got a rectangle that its sides be x and y, and we're dealing in meters. And I know that the area of that rectangle is 216. It's enclosed by a fence and divided into two equal parts by another fence parallel to one of the sides. So let the internal fence be parallel to the side y. So I have three fences of length y, two fences of length x. I want to know what dimensions for the outer rectangles. So I want x and y so that I have the smallest total length of fence. So I need to write down an expression for the total length of fence. So my fencing length in terms of x and y. Ooh, I have 2x's plus a 3y. Next step, as we've been doing before, is to use only one variable. Let's go with x. That's 2x plus 3, and y is 216 divided by x. So I get f of x is 2x plus 648 over x. All right. The next step, as usual, is the domain. And once again, you can see I cannot have x equal to 0. It will make both y and f of x undefined. It will make them infinite quantities. It's one thing having 0 and for one of your quantities, but it is really a no-no to have it infinite. So let's go back. My domain, the best we can do is x is greater than 0. Cannot use the EVT because it is not a closed interval. And I am back to doing this like the previous problem. Okay, let's go on to example 9. An open top, so there's no top to this cylindrical can. And it'll hold 1 liter, which is 1,000 cubic centimeters. That's a volume unit. So I know that the volume of this can is 1,000 cubic centimeters, and you are told the volume of the cylinder is pi r squared h, and because it's cubic centimeters, our units are all going to be in centimeters for length. What dimensions use the least amount of metal? Well, the least amount of metal, in terms of the weight of the metal, will be when I minimize the surface area. So my task here is to minimize the surface area. And the surface area of an open top cylinder is pi r squared, that's the bottom, the base, plus the curved surface area. So that bit is the curved surface area, and there's the base. So I want to minimize S, which is in the terms of variables R and H, pi r squared plus 2 pi r h. Once again, we want to write this in one variable only. Let's go with r. H is the most convenient choice to replace. I know that H is 1,000 over pi r squared. So S in terms of r is pi r squared plus 2 pi r. H is 1,000 over pi r squared. Woohoo, the pi's cancel and r cancels. I get S in terms of r is pi r squared plus, what's that, 2,000 over r. Ooh, that r in the denominator tells us one thing straight away, that I'm looking for the domain, I'm looking for what's true about r. R cannot be 0 because it makes both H and S infinite, makes them not exist. So R is greater than 0 is our domain. There's no maximum value for R. What happens if you look at the expression for H is R gets bigger and bigger and bigger, just H gets smaller and smaller. It's not very realistic, but it's not mathematically impossible. Again, you cannot use the EVT because you don't have a closed interval. You work the problem as before. Okay, and a quick reminder that often it is useful to rewrite our expressions for whatever it is we need to differentiate in a different fashion to make it easier to differentiate. Okay, last problem. I have got a 20,000 cubic meters. That's another volume unit. So it's an open-topped rectangular top. It's an open-top rectangular tank. So with a square base, x meters by x meters, a square base, that's measured in meters, and the height of my tank is y meters deep. Okay, and the volume is 20,000. How do I find the volume of a box? Length times base times height, so x times y, x squared y is 20,000. That's what I'm given. The cost per square foot for the material for the sides of the tank is $1,000 per square meter, and I'm given the cost is $800 per square meter for the base. Find x and y that minimizes the cost of the materials. So I need to minimize the cost function. C in terms of x and y is going to be equal to what? Okay, the sides of the tank. So let's look at one of the sides of the tank. Each side has got an area of xy square meters. There are 4 equal sides. So I've got 4 xy's. That's the number of square meters for the sides. And each square meter is 1,000. My answer is going to be in dollars. And then for the base, the area of the base is x squared square meters, and for the base, each square meter costs $800. So this is the cost in dollars. So that's my cost function. It is 4,000 xy plus 800 x squared. That's my cost function in terms of both variables. Let's get rid of a variable. It looks once again as though y is the most convenient one to get rid of, isn't it? Let's have a quick look. Y is 20,000 over x. So I have 4,000 x and y, over x squared, isn't it? Y is 20,000 over x squared. X cancels with one of the x squareds, and I get, 8. And a total of what, 7 zeros over x plus 800 500x squared. Once again, now that I have that x in the denominator, I know I can't have x equal to 0, and my domain is again x is greater than 0. And I work the problem just like the previous ones.